Okay, welcome to the screencast for worksheet 13 part 2 on alkenes. So question 1 is question on cracking, which it was covered in the alkene section, which is why I didn't ask you to do this part of the question. So question 1a, on cracking, the products obtained will depend on the actual conditions used. However, we will always get an alkene. Write balanced chemical equations to show how the cracking of C4H10 produces hydrogen. So how do I do this kind of question? First, you know that there's C4H10 and you know for sure that hydrogen is produced. If we are to subtract 2 hydrogen from C4H10, you get C4H8. Okay, so but it's not possible for you to just take out the hydrogen, right? Remember, when hydrogen is a product, 2 alkenes are formed. So the shortest alkene that's possible is 2 carbon. Therefore, the only possible answer is C2 alkene being formed. Okay. Some of you wrote state symbols. Note that your butane is a gas at room temperature and pressure. Okay, like here. Okay, note that it's a gas, not a liquid. Only the longer chain hydrocarbons are liquid at room temperature. Next, ethane. So for this, you know that C4H10 is the reactant. Ethane C2H4N 2N plus 2, so is 6. Then you just think, how many more carbon and hydrogens do I have? So you are left with 2 carbon and 4 hydrogen, which is ethene. Some of you just, I don't know, give up and just write 1 ethane, then, I don't know, somehow force it there. Okay, so make sure that you read the question carefully. So for this kind of cracking questions, make sure that your products, the sum of the carbon and the sum of the hydrogens, give back your initial alkane. Again, an alkane can become alkane plus alkene. If not, the alkane will give you alkene plus alkene plus hydrogen. Hydrogen gas, so H2, not just H. Yeah, I think 1 or 2 students also just wrote 2H. Okay, Sec 4 already, you should know that hydrogen doesn't exist as just a hydrogen atom. It's always H2. Okay, why is it important in the petrochemical industry? Mainly, it is to make smaller hydrocarbon molecules, which are more useful, okay, to make useful products. So if you state the use of them, I will accept. Some of you say that it is to form petrol. So I think what you need to elaborate on the answer is, what exactly is petrol? So petrol is actually a short chain alkane. Okay, so it's the whole purpose is actually to make smaller hydrocarbon molecules, be it alkane or alkene, because they are more useful rather than a long chain alkane. Draw the full structure. Oh, I think this is a different question from yours. Yours is draw all the isomers for C4. Yours is to draw the isomers for C4H8, right? So you can have build 1 in, build 2 in. You can also have 2-methyl, build 1 in. And some of you also drew this, which is your chlorobutane. Oh, not chlorobutane, cyclobutane. Okay, but if they ask you what are the possible products from this cracking reaction, if they ask you for this particular C4H10, note that only this and this is possible. Okay, we can't get a methyl group as a side chain unless the starting compound is already somehow branched. Okay, and it's not possible for us to get a cyclo product. Okay. Next, name the organic products formed when excess butane is added to chlorine gas in bright sunlight. What type of reaction is this? So this is a similar question to your quiz. Again, when there's excess butane, you should think of only mono or di substituted butane at the most. Okay, now that chlorine is used, so it should be chloro something. Because the chloro group can be at the first or second position of butane, we need to specify the exact location. So 1 chloro or 2 chloroputane. Okay, so as you write substitution, even without the word free radical is also marked as correct. So 2 products, you must say both. Okay, again, it's organic products. So if you wrote HCl, hydrogen chloride, it will be marked wrong. If you write hydrochloric acid, it is even more wrong. Okay, because the organic product, the product form is hydrogen chloride. This is hydrogen chloride. It is a simple covalent molecule. It is only hydrochloric acid when it's dissolved in water. Okay. Some of you also wrote octane. Octane is a possible product, but it is a lot less likely to be formed as compared to 1 chloro or 2 chloroputane. So the major products are 1 chlorobutane followed by 2 chloroputane. Then there will be a lot of sub-minor products such as octane. Maybe there's some tri-substituted or di-substituted butane that's of a much smaller quantity. Okay. E, draw the full structural formula of the organic compounds formed when but2-ene reacts with the following reagent. Give the conditions necessary for the reaction to take place. So again, you should draw out but2-ene. But2-ene, so the CC double bond is at the second CC bond. So it look like this. If I add steam to it, HOH, how should it look like? Okay, this bond will break, this bond will break, and it will join like this. Regardless of which way you position the water molecule, it's always butyl-2-nol. Okay, note that it's not possible for butyl-1-nol to form, because for butyl-1-nol to form, the CC double bond must be at the first position. Okay, so catalyst, phosphoric acid, 300 degrees Celsius, 60 or 63 atm. Okay, bromine gas, again, let me copy and paste this. If I will have to the butene, then I'm adding a bromine molecule across it. Okay, what will happen is this double bond will break, this bond between bromines will break, and it will form these 2 new bonds. So you always draw the original in pencil, you erase the double bond, and you add whatever stuff across that double bond. Okay, and it should be clear to you that the product is this 2,3-dibromobutane. Okay, so this is just at the room temperature and pressure. I didn't mark for absence of UV light, so If you write, that will be even more correct. Lastly, hydrogen gas. Again, erase this double bond. We add the hydrogen gas across. Okay, break this hydrogen bond, join it together, you get butane. Most of you got butane. Some of you wrote the conditions wrongly though. It's nickel catalyst at 200 degrees Celsius. So the equations show how margarine is produced from vegetable oil. You will see that there's this CC double bond, and then you're adding these two hydrogen here. Okay. Now, some of you thought that the compound is just these 6 carbon and with those amount of hydrogen. Note that there's this bond where it didn't show where your carbon is connected to. This implies that the whole molecule is larger than this. Okay, this is only one section of the vegetable oil. Okay, what type of reaction takes place between hydrogen and vegetable oil? Okay, when they ask you for type of reaction, you have to write down the following types of reaction. 1. Addition. 2. Substitution. 3. Oxidation or reduction. 4. Elimination or what we call condensation. Okay, elimination and condensation, you will learn this in esters. Okay, so what is the type of reaction? A lot of you wrote hydrogenation, which is correct because that's the name of this reaction. However, that's not the type of reaction. It's like if they ask you what type of food do you like to eat, you say Japanese food. You don't say chawamushi. Okay, that's too specific. Okay, when they ask you a type, they want a general classification of what type it is. Okay, so what type of reaction is this? It's an addition reaction. So mostly the reaction of alkene is an addition reactions because it has the CC double bond for things to be added across. How do you know this is addition and not substitution? Note that there's no other product. Again, I'm adding one guy and one girl who are single together to form one couple. Okay, if it's substitution, the girl already has a boyfriend, then he kick out that boyfriend and join with another single guy to form a new couple, but that's at the expense of the previous boyfriend. Okay, substituted the boyfriend. So next, what is the purpose of nickel in this reaction? It acts as a catalyst to speed up the reaction. Most of you got the catalyst correct. Why is it in powder form? It is to have a larger surface area to speed up the reaction. So there are two keywords here: larger surface area to volume ratio to speed up the reaction. Okay, so you must have the part about speeding up the reaction. If you talk about higher frequency of effective collisions, all that is fine, but your conclusion must still be hence increasing the rate of reaction. Okay, lastly, okay, some students were unable to do this question. They left it blank. So what they are asking is this: some vegetable oil molecules contain more than one CC double bond. The number of CC double bonds can be found by reacting the oil with iodine. So iodine is a halogen. Again, we are adding halogen across the CC double bond. It's the emergency exercise now, so I'll stop the recording here. Okay, I'll join you again later. Okay, so I'm back 2 days later. So let's continue with this question. First off, let's highlight some of the keywords. The number of CC bonds can be found by reacting it with iodine. It's in the same way as bromine. So I have 0.5 moles of the oil. Mass increase of this when shaken with excess solution of iodine. So how do we attempt this question? Now, first of all, you must ask yourself, how does bromine react with CC bonds? So when the bromine approaches a CC bond, what happens is it will add itself to the bond, like so. That said, with one CC bond, you'll see that 1 molecule of Br2 is used. So therefore we can use the same analogy, and we know that for iodine, for 1 CC double bond, we will need 1 molecule of I2. So that's how we can begin to calculate this question. First off, this mass increase, you must ask yourself, where did this mass increase come from? Now, the mass increase comes from the addition of these iodine molecules, right? So what we can do is we can calculate the number of moles of I2 used such that there's a mass increase. So 25.4 divided by 127, which is the amount of iodine, times 2. That will give me 0.1 mole of iodine. Okay, so remember that 1 mole of iodine equals to 1 mole of CC double bond. Let me write down. So therefore, what is the number of CC double bond in this? In fat, oh not fat, sorry, this is a vegetable oil molecule. This will be 0.1 divided by 0.05. Because 0.05 is the number of moles of oil molecule, the number of moles of carbon double bond is 0.1. To find out the number in each molecule, you just divide by it, and you should end up with 2. Okay, if you still have a question regarding this question, please raise it up in class. Oh, this one was the last time we finished this already. Okay. Next, question 4. Question 4 was a question that I said, haha. So, after learning the reactions of alkene, Jane wanted to try it herself. To a sample of propene, she added hydrogen bromide. So first, note the reactants. I use bromine and hydrogen bromide. What type of reaction is this? Okay, again, when they ask for type of reaction, you are to name one of the 4 types of reaction and not just state the name of the reaction. Okay, so look out for the keyword type. When they say type of reaction, it's addition, substitution, oxidation reduction, or condensation elimination. Not the specific name. Most of you wrote hydrohalogenation. Okay, that's the name of this reaction, but not the type of reaction. Name the expected products in the space. Again, you need to specify 1 and 2. Some of you wrote bromopropane or 1,2-dibromopropane. So again, let me draw propane. Propane looks like this. Right? When I add HBr, how do I add it? Now we can add it in, let me copy and paste first. Now I can add it in 2 ways. I can add it like this, BrH, or I can add it like this, HBr. Okay, either way, you should know that the type of product form will be this. Or this, right? So in the first case, we have this will be known as 1-bromopropane. Here it is 2-bromopropane. So that's why you should expect these 2 products, 1-bromopropane and 2-bromopropane. Strangely, she only got one product from this reaction. Okay, so which is the product? Okay, I never say, but she checked on the internet. She found something called Markovnikov rule that can explain this phenomenon. When an unsymmetrical alkene reacts with a hydrogen halide to give an alkyl halide, the hydrogen adds to the carbon of the alkene that has the greater number of hydrogen substituents. So H add to the one with more H, halogen add to the one that has fewer hydrogens. Okay, to illustrate this rule, there's a few examples. Okay, example number 1, you note that the hydrogen here is added here, which is added in the first position. Now, in the first position, how many? Okay, so first let's look at the CC double bond and count. Here, there's 1, 2 on one side. The other side, I have only one hydrogen attached to the carbon. So the side that has more hydrogen is the first carbon. Therefore, it is attached to the first carbon. Now next, again, let's look at the CC double bond. Here we have one hydrogen attached to one side. On the other side, we see a methyl group and there's no hydrogen attached to it. Therefore, again, over here, you will see that the hydrogen is attached to the side that has more hydrogen and the other substituent is attached to the other carbon. Lastly, you see that here I have one H, the other side I also have one H, since they have equal number of hydrogen substituent. Okay, you will see that we are adding the we have two products, so two things can happen because since they have the same number of hydrogen substituent at each side, there's no preference. Okay, Markovnikov rule wouldn't predict, so both will occur. So we can either have the hydrogen, we can either have the chlorine here in the second position or the chlorine here in the third position. Okay, so next we need to predict the product of the following compounds reacting with HBr. Again, first you see which is the side across the double bond, which is the one that has more hydrogen. You know that they have the same, so theoretically you should have two products. Now, which is what a lot of you drew, and you drew this other product like this. Okay, now why is this wrong? It's because, can you see that these two molecules, they are the same? Okay, that's because this is a symmetrical alkene. So in the case of a symmetrical alkene, you will only end up having one product because no matter how you add, you will end up with the same product. Next, okay, again, let's color. This side, I have one hydrogen. On the other carbon of the CC double bond, there is 0 hydrogen. Okay, it's attached to a methyl group. Therefore, the side with more hydrogen is this side. I should add a H here. I should add a bromine here. Yeah, I ask you to draw with bromine. HBr. Yes, the thing is, right, it says HBr, so you should draw a bromine inside for me. But some of you drew a chlorine, which I don't know for what reason. Okay, so that's how I end up with this answer over at the right hand side. Okay, the hydrogen should add to the one, the side that has more hydrogen substituents. Okay, some of you just drew it this way instead, the H here and the Br here. I think a lot of you have the tendency to just draw HBr as just like, because it's HBr, H should always be on the left hand side, Br on the right hand side. But that's not true because molecules can turn, okay, can flip, turn, rotate. So it's not true that the H must always be on the left-hand side. Okay, that's just when we write equations. Then lastly, let's see over here, we have one H here, across that double bond. On the other side, we also only have one H. Therefore, I can add it either add a H here and a BR here, or I can add a BR here or a H here. Okay. Does it give us the same product? So after you draw it out, you must check, do they give you the same product? No. Why is that so? Without the existence of this methyl group, actually they will be the same product. But since there's this methyl group, they are not the same. Here, this is 1, 2, 2 carbons away. Here, it is 1, 2, 3 carbons away, the bromine group. Therefore, they are not the same compound, and we must draw both. Okay, to check if it also applies for the addition of steam, Jane reacted steam with butene and found that she only obtained one product. She then concluded that Markovnikov rule also applied to the addition of steam in alkanes. So first, draw out butene. Butene means the double bond is here. And then we fill in the hydrogens. Make sure that each carbon only forms 4 bonds, no more, no less. Now, how do we add water to it? I can add water like this, HOH. Or I can add it like this. Or I can add it like this. Right? Okay, so since there's only one product, it means that it does satisfy Markovnikov rule, right? No, because again, note that these two are the same product. They are both butatunol, okay? Both butatunol. So, do you agree with the conclusion? Why or why not? You can explain it in a few ways. First, you can explain that the two carbons have the same number of hydrogen atoms. So, we can't observe Markovnikov rule. Okay? We only form one product because butene is a symmetrical molecule. And no matter how we add water, it will still give the same product, butatunol. Okay, some of you said that because water is not a hydrogen halide, that's why it doesn't work. Okay, so actually what she wants to do is to check if this rule of the H adding to the C with more H also applies to the addition of steam. So she's checking if that's the case. So you can't say that steam is not a hydrogen halide. Of course she knows. Okay. So what you need to do is you must say that her choice of material is wrong because it's a symmetrical molecule. No matter how we add, it will give us the same product, okay, butatunol. Therefore, we can't observe if Markovnikov rule is right or wrong. Okay, so that's all for this screen class. If you have more questions, please ask me in class.